So from last time we left off, we talked about a couple forces. Talked about the difference between inter and intramolecular forces. And now we're going to get more into the types of intermolecular forces. So this is a quick sort of diagram. There are two types of intermolecular forces. We have dipole-dipole forces, which are just similar to hydrogen bonding, which is a hydrogen bond. And then London dispersion forces, called London dispersion forces. So the dipole-dipole forces, you can see on the left side, the interaction of two polar molecules. Is water a polar molecule? Is water a polar molecule? Yes. So I'm going to draw a water molecule in the top right corner. Hydrogen, oxygen, and hydrogen. And we have our dipole moment pointing up towards the oxygen, the more electronegative. Right? So we have a partial negative by the oxygen, and then a partial positive on the hydrogen side. So if we look in the bottom left now, these are two interactions. We have the partial positive side interacting with the partial negative side. Those would be dipole-dipole forces. Hydrogen bond is when we have hydrogen interacting with the oxygen. That's like water. Now the next one, London dispersion. If you notice, the molecule they have up there is H2. Does that have a dipole moment? It's the same atoms, so the electronegativity difference is 0, so there's no dipole moment. But we can have what is called an induced dipole. What do you notice about the sort of densities on these two? This left side is a darker blue than the right. So the electrons have shifted to one side. Because these electrons, that electron cloud, the probability has shifted, it's going to have an induced dipole, and one side is going to be partial positive, one side is partial negative. How does this happen? Something induces that dipole moment. So a magnet or some sort of interaction between some other molecule. What this does is it causes a chain reaction. So on the left side, you see how we have that induced dipole. And then on the right side, now those electrons are going to be drawn to that positive side, and that's going to induce a dipole in that molecule, so on and so forth, and have a chain reaction. Which is stronger? What do you guys think is stronger? The dipole-dipole forces. So remember our dipole moment, right? We talked about this in water. We have our arrow, partial positive, partial negative. We can use an electric field, this is like a magnet, to induce that dipole. So there's a positive side, positive charge, and a negative charge. And they attract each other. Positives attract the negatives, negatives attract the positives. Then we get an interaction. And these are only 1% as strong as a covalent or ionic bond. Because remember, the covalent and ionic, when we're boiling water, are we breaking the bond between the hydrogen and oxygen atom? No, right? That takes a lot of energy. But what are we breaking? What bond? The hydrogen bond between the hydrogen and oxygen of different atoms we're breaking. We are not breaking the bond between the hydrogen and oxygen of the same atom. So now, hydrogen bonding, another type of dipole-dipole interaction. This is the strongest dipole-dipole interaction, hydrogen bonding. How much energy do we have to put into water to get it to boil? A lot or a little? A lot, right? It takes a lot of energy to boil water because we have hydrogen bonds inside that water holding those water molecules together. That's why we got to put in a lot of energy. And then that hydrogen bond doesn't just have to be between oxygen and hydrogen. It can be between any, what they call a highly electronegative atom. So nitrogen, oxygen, and fluorine. Where on the periodic table, just generally, do we have our most electronegative atoms? Yeah, top right. Electronegativity, top right. So fluorine, oxygen, nitrogen, chlorine, all that type of stuff can form hydrogen bonds. Any questions on this so far? It's pretty straightforward, right? So now London dispersion. This is when we talked about inducing a dipole. We can induce a dipole, an instantaneous dipole, that is very similar if we had a, say, water that has a permanent dipole. So if you look on the picture at the bottom here, we have atom A. We have induced a dipole on atom A. I'm going to draw a magnet here. We had a magnet that induced this dipole. And if you look on the right now, atom A has that dipole, now atom B does. Because this positive side of atom A has attracted some of these electrons on atom B. It's attracted those electrons right there. And now, this side of atom B has more electrons in it, has a partial negative charge, and the right side has a partial positive. So it causes a chain reaction. So if we had a jar of all these types of atoms, and we tossed, say we could induce a dipole, and then just toss that atom inside of the jar. Eventually, all of those atoms would just start cycling through these dipoles, and would just continue. But one thing I want you guys to notice, very important here, I'm going to underline it, all molecules. All molecules. Because remember, London dispersion is an induced dipole. So if something has a dipole already, you can still induce more of a dipole. So it occurs in all molecules. So if I give you a question on the test, big hint, how many of these have London dispersion forces? You should be able to answer that. Okay? So does water have London dispersion? Does HCl? Does CO2? Does O2? I think you get the point. So which molecule is capable of forming stronger intermolecular forces? And why? H2O, good. And why? So what type of bond do we have, or what type of force do we have for N2? London. What type of force do we have for water? London and hydrogen. Good. So another one. You guys should be able to answer this one, right? How many of the compounds above exhibit London dispersion? 0, 1, 2, or 3? Good. All of them. So now last little bit for today. Colligative properties. So these are properties that are affected by the number of solute particles. What's a solute?
Something that's dissolvable in water.
Good. Something that is dissolvable in water. So what's a very common? So salt. We put salt in water. Put salt on our food. Makes stuff taste better. When mama's cooking is bad, you put salt in it to fix it. But so colligative properties is what's listed up there. Vapor pressure, boiling point, and freezing point. Right? Now, we're going to look at how does adding a solute or salt or anything affect the vapor pressure, the boiling point, and the freezing point. Boiling point is when the vapor pressure of a liquid equals the atmosphere pressure. Okay? Boiling point is when the vapor pressure of a liquid equals the pressure of the atmosphere. We'll get into that in a second, I'll show you. Right here, vapor pressure. Vapor pressure is the pressure exerted by a particle escaping from a liquid, trying to get out into a gas phase. And that boiling occurs when the vapor pressure equals or exceeds atmosphere. So that means, if we're looking at this diagram right here, we have, let's pretend all the red is water, and all the blue is just like salt dissolved in there. And we're just going to call these dots air pressure, air molecules. Even though we know air is a mixture of nitrogen, oxygen, CO2, and all that, we're going to just call these little green dots air molecules. These air molecules are pressing down on this liquid. It's pressing down on this liquid with a pressure, and that is our pressure of the atmosphere. So those air molecules are pressing down on that liquid. So when our vapor pressure equals or exceeds the atmosphere pressure, then right here we have molecules that are able to, water molecules that are able to escape and become in the gas phase. And now we're going to get to that because adding a solute is going to lower the vapor pressure. Because these red water molecules are trying to push up and out. They're running into the solute, the blue particles. They're running into that salt. And it's a lot harder for that water molecule to leave the liquid state when it's interacting with those salt or the solute inside the water. And you see how the solute covers some of the surface area. See these blue molecules here at the top? That's covering some of the surface area. So those water molecules cannot leave the liquid state. That's why we add salt to our water if we want to boil. Say we want to make pasta here at Elevation in Colorado. We add a little bit of salt, so that's going to increase our water temperature, and it's going to cook our pasta faster. What happens is, remember our heating and cooling curve? We get to a plateau. We get to that plateau, not last longer, shorter. Or not shorter. When we get to that, we add that plateau with salt water, we can't get, with just water in the plateau, as soon as we get to the plateau and we keep adding heat, the temperature of the water does not increase. Because it's a combination of the vapor and liquid, right? So what we do is we're going to, adding that salt increases the plateau, so now the water gets to a higher temperature before it boils and then gets stuck at the plateau. Does that make sense? So right here, the boiling point. We just talked about this with water. We add salt to our water to cook pasta. Because we're going to add that salt, it's going to decrease the surface area of those water molecules so less water can escape into a gas phase. It's going to trap that water inside the liquid. We can add more heat, and that liquid's going to heat up more before it tries to boil. So the higher number of salt particles in a solution creates a higher boiling point. Freezing point depression. Freezing point depression. What is this? When you hear freezing point depression, what do you think happens? Lower the freezing point. So what do we put on the roads when it snows outside? Salt, dirt, pretty much anything, right? Because it's going to gravel. It's going to lower the freezing point. So these solute particles, when we dissolve salt in water, those solute particles are going to interfere with it's going to interfere with all the other, say, water molecules, and it can't form that nice crystal structure. It can't form that nice crystal structure. We have a beaker with water, a bunch of H2Os, and we have dissolved some salt. We dissolve salt inside that beaker. And the chlorines and those sodiums are going to get in the way of those water molecules from forming those strong hydrogen bonds that then form that crystal structure of salt. Not salt, water or ice. So now, the phase diagram. You guys should know this, the phase diagram. This is for water. Not exactly water, but this is what it looks like. So we have our solid region, our gas region, and our liquid region. And at this point right here, that is where all three exist at the same time. Now in our heating and cooling curve, we had a constant pressure, right? We had a constant pressure. Now here, we can increase pressure, we can change our pressure, and we can change our temperature. So at that point right there, we have solid, liquid, and gas occurring at the same time. So that means we have some molecules that are gas, some that are liquid, and some that are solid. Now, right here, are there some water molecules above the water in the water bottle? So we have liquid and gas occurring at the same time. So now, and then as we go up this curve, we get to the supercritical fluid where it's a combination of gas and liquid. So now I want you guys to think about at your table, draw this curve, and then I want you to draw another curve as to what it would look like if we added salt. So you know that what happens to the boiling point? Boiling point increases. What happens to the freezing point? What happens to the vapor pressure? Here's the answer. So what happens is the vapor pressure of the liquid, what happens to it? We talked about colligative properties. What happens, Carlos? The vapor pressure, it decreases. So here's the decrease in vapor pressure. Now, the solid and liquid, does it for temperature? When we add salt, does that increase or decrease the freezing point? It decreases it, right? Does the melting point increase or decrease when we add a salt? So we're decreasing the temperature at which it melts. So we add salt to roads to prevent ice from forming, because ice is going to form at a lower temperature. That's why our line for the line between solid and liquid shifted to the left, and then our liquid and gas line went down, because the vapor pressure decreases because we have more particles holding that water inside the liquid phase. So the gas phase, then that line is going to go down. Everybody see that?